So we've got Amy Gandy, who's from the University of Sheffield. Like I say, Amy's one of the technology platform leads for the Royce Institute, so at Sheffield University. And today she's going to be talking about grazing incidence, XRD, and characterisation of ion irradiation damage using that.
Yep.
Brilliant. Thanks, Amy.
Yeah, of course.
Just before we continue, did anybody lose a pair of headphones yesterday? Excellent, that's fantastic. Amy.
Okay, thank you. Thanks ever so much. So as Rob's already introduced me, I'm Amy Gandy. I'm a senior lecturer in nuclear materials engineering in the Department of Materials Science and Engineering at the University of Sheffield. I'm also one of the Royce technology platform leads, specifically in advanced characterisation of radiation damage and materials. So if any of you would like to know more about the equipment that we have specifically at Sheffield to characterise radiation damage in your materials, we can also do active material characterisation as well as non-active material characterisation. Please come and talk to me either over lunch or get in touch with me afterwards. So today I'm going to talk to you about one of these characterisation methods, which is using X-ray diffraction in what we call grazing incidence mode. And this is specifically then to look at ion implantation induced damage in our materials. Okay, so as we know, our particulate radiation that can exist in a range of nuclear applications and non-nuclear applications, so, and I mentioned space applications as well. Those particulate radiation can interact with the atoms in our material, displacing those atoms, changing the internal structure of the material, and we all know that that can lead to a change in the properties and therefore the performance of our materials. For a lot of us, we don't work on active materials, especially those of us who are developing novel materials, so we want to do a scoping exercise before we go and irradiate our new materials with neutrons or other radioactive sources. And therefore we use ion implantation, so non-active ion implantation, in order to induce those same types of structural damage. So I think yesterday you had a talk on ion implantation, so you know very well the limitations of ion implantation, which is why I said it can replicate-ish the damage that's produced by neutrons and other types of radiation, but ultimately it can induce structural modifications as well as form radiation-induced defects like dislocations, like Jack was talking about, gas bubbles, secondary phases, precipitates, and all the things that we've seen wonderfully in using TEM. So yeah, when we do ion implantation, we're often implanting the surface of our bulk material with ions of a few hundred kiloelectron volts to a few MeV of energy. Of course, there are special facilities that allow us to go to gigaelectron volts of energy, and some facilities that allow us to go to really low energies if we're looking at plasma surface interactions for fusion materials, for example. But typically we're in the range of about 1 MeV of a heavy ion if we want to simulate things like alpha daughter recall nuclei, if we're looking at nuclear waste forms, or also the energy transferred from our neutrons if we're just looking at in-reactor materials. So this is a typical shim simulation, which you should all know very well about how to create, thanks to Rob's talk yesterday. And it shows us that a typical heavy ion irradiation, this is 5 MeV gold, into one of our alloys that I'll introduce you to in a few slides' time. That actually induces damage up to about a micron, so relatively surface sensitive. Typically the maximum amount of damage is about 500 nanometers below the surface. Now, cross-sectional TEM is a wonderful tool, and I've used it extensively, as have many people that I've worked with, in order to characterise and investigate the types of damage that's produced. But as I'm sure those of you who do TEM are very aware, it takes a very long time, not only to learn how to do just basic TEM, but then you've got to learn all the weak beam dark field and 2-beam analysis and Fresnel contrast if you want to look at helium bubbles, but also to prepare your samples. So we're talking about months, if not years, to become really proficient to be able to look at damage in our materials. What is if there was another technique that we could use that allowed us to rapidly scan loads of different materials in a matter of a few hours to have a look at whether there are any implantation-induced structural modifications to our material? Well, there is, and it's called X-ray diffraction. So that's what I'm going to talk about today, how we can use X-ray diffraction to look at the damage that's produced in our material, specifically in the surface damage produced by ion implantation. But before I go specifically into the grazing incidence mode, I do want to give you a bit of a background to X-ray diffraction. You've been hearing a lot about TEM, and maybe some of you are not particularly familiar with XRD. But also it's good to kind of understand the basic principles behind X-ray diffraction to know why the standard diffractometers that we have in many of our labs are not suitable to probe surface damage layers, and therefore why we need to have specific, more advanced diffractometers that allow us to look at the surface damage layers. So, quite simply, X-rays or electromagnetic radiation, their wavelength happily is quite similar to the interatomic separation, so the interatomic spacing between lattice planes in our crystals. And because of those similarities in wavelengths and size, that allows the X-rays, the waves, to interact with the planes of atoms in our crystalline material, producing interference fringes, or interference patterns, which are essentially a diffraction pattern. And we're able to detect and measure that diffraction pattern, and that gives us information about those crystal structures, about the crystal planes that were diffracting those X-rays. So this is an example of a diffraction pattern that we can get from XRD. Each one of these peaks corresponds to a crystal plane in our material. This is a really nice body-centered cubic crystal lattice. We'll see some examples of more complicated ones on the next slide. So X-ray diffraction then can be used to determine a wide range of different things, and this isn't just in grazing incidence mode, this is just XRD in general. So if you are making new materials or understanding how by heating or applying pressure to your material is going to change the internal structure of your material, you might want to use XRD in order to determine that. So I've put a list here of the things that you can do with XRD. So you can identify phases. For example, is my material body-centered cubic? Is it face-centered cubic? Is it a weird tetragonal intermetallic phase, which is what we keep getting in our novel materials? And the way in which we identify these phases is we take our diffraction pattern that we created using XRD and we compare it to a wide range of other diffraction patterns that you have in a database. We use the ICSD database, which is just an international database of all different crystal structures. If you publish a paper within which you have a crystal structure, you can add it to this database. So you have software that allows you to search through this database and literally match your diffraction pattern to diffraction patterns of known materials and known structures in the literature. You can also use XRD to determine the crystal structures of unknown materials. There, of course, you're not going to match directly onto a material with your material because you're making a material that no one's ever made before, but you're able to do some fitting within the software that allows you to say, hey, what is this crystal structure, even if the composition is different? So XRD allows you to characterize known materials, but you could also get a lot of information from unknown materials if they're materials that you're developing for the first time. So what it can also tell you, because these peak positions, these peak intensities can actually give us an awful lot of information within our crystal, it can tell you about changes to unit cell parameters, so cell volume, so volume expansion as a function of whatever you've done to it, heating, pressure, irradiation damage. And it can also tell you about the crystallite size, so the broader these peaks, typically, not always, but in some cases, the smaller the crystals within your material if you've got a polycrystalline material. It can also, and this is the example we have here, tell you about temperature-induced phase transformation. So whilst this isn't grazing incidence, one of the things that we can also do using the same diffractometer is heat your material in situ whilst taking diffraction patterns. So here, this is at room temperature, this is that nice body-centered cubic crystal structure, wonderful. Heat it up to 1,000 degrees Celsius at different temperatures, so taking diffraction patterns at different temperatures. And we can see that there's a phase transition from one crystal structure into another crystal structure. We did a lot of peak fitting offline with this, and we found that this very complicated crystal structure is our tetragonal sigma phase. It's a brittle intermetallic phase, which is not a reversible transition, unfortunately. Okay, so that's what you can do with XRD. So how on earth are X-rays produced in our diffractometers? This is important because you need to understand about the X-rays, the nature of the X-rays that are produced to be able to input the correct values into the equations that I'm going to introduce you to later for the grazing incidence geometry. So basically, X-rays, very similar, if not identical to how electrons are produced in a TEM. You produce electrons in our diffractometer by heating up a filament, for example, a tungsten filament. You do that by applying a voltage. Once the work function is reached, you then emit electrons, a beam of electrons. And those beam of electrons are then directed onto a metallic target within your diffractometer. We typically use copper in our diffractometers for a wide range of reasons. Cost is one of them, it's cheap. And what happens then are the X-rays then interact with the the electrons interact with the core shell atoms of our copper target, promoting those core shell electrons, ionizing them, which leaves a hole in our atom, in our metal atom. And then what happens when you have a hole in your shell of electrons is an electron from a higher energy level drops back down to fill that hole. But when that happens, it emits electromagnetic radiation in the form of an X-ray. And these just show you some of the transitions that happen. So this is our core shell electron. We call it the K shell. Then we have the next shell up, our L shell. Then we have the next shell up further and further towards the valence shell electrons. And we have some transitions where our electrons are dropping from our L shell down to our K shell. We call them the K alpha transitions. And sometimes we have electrons from our M shell dropping down to our K shell, and we call them the K beta transitions. So what happens then is when these transitions occur, an X-ray is emitted, and that X-ray has an energy and a wavelength that's very specific, and it's determined by the difference in energy levels between the transitions, so the difference between the M and the K or the L and the K. So in our copper source, what does that mean? Well, our K alpha, which is where we go from our L to our K shell, has a wavelength of about 1.54 angstroms. Our K beta has a wavelength of about 1.39 angstroms. Now, in order for our diffraction patterns to occur and to be meaningful, we actually need to have monochromatic X-rays, which means we need to have one wavelength, one energy. So what we have to do in our particular source is we need to suppress this K beta radiation. We do that by adding in a filter. We actually use a nickel filter in our diffractometer. And that's because the absorption edge of nickel, and that is the energy where the electrons in the core shell of our nickel atoms absorb X-rays, actually corresponds to energies around our K beta radiation, which basically suppresses the K beta radiation coming out. So it only allows the K alpha X-rays to be emitted. It doesn't fully remove K beta. There's always a little bit there, and that's something to consider if you're doing some really high resolution XRD. But for what we're doing, that's fine. Okay, so how do those X-rays that we've now produced, our lovely K alpha radiation, how do they then go into our material, interact with the atoms in our material, and cause diffraction patterns that then tell us something about a material? And it's basically because the electromagnetic radiation, it is a wave. So X-rays are waves, and they interact with each other just as waves would normally do. So you can get things like constructive interference, where you have two waves that have the same phase and the same wavelength, constructively interfering, so basically building up, increasing the wave pattern, as you can see here. You can have constructive interference, which is when they're out of phase and they cancel each other out, which is what you can see here. So diffraction patterns are only produced when constructive interference occurs. And constructive interference only occurs when our X-rays remain in phase and they're coherent with each other after the interaction with the atomic plane. So when the X-rays come in, they interact with the electrons surrounding our atoms, they get absorbed and they get re-emitted. If they get re-emitted with the same energy, they're then coherent. And if they haven't scattered inelastically, then they can remain in phase. And that allows the X-rays to combine and constructively interfere, which is what gives us our diffraction patterns. But we find that only happens when the X-rays are scattered through very specific angles. This can be described by what we call Bragg's law. So a lot of you may know this already, especially those of you who work on electron diffraction. And this tells us how the wavelength, so the X-ray wavelength, is related to the interatomic spacing between our lattice planes and the angle through which they're scattered, which allows constructive interference to occur. So, as a consequence, we're able to use Bragg's law to predict which set of interatomic lattice planes are going to diffract, resulting in a diffraction pattern, so interfere constructively, resulting in a diffraction pattern. So basically, we can measure the different angles at which constructive interference occurs, so this theta. And everywhere where constructive interference occurs, we get a peak, because that's where our X-rays have constructively interfered, so diffraction has occurred. And these peaks then correspond to different crystal planes within our lattice. So there's an awful lot of stuff online. We've got a lot of resources at Sheffield as well that allows you to calculate where these different peaks correspond to in terms of our Miller indices, so our lattice planes that have resulted in the production of these diffraction peaks. So I won't go into that now. As I say, it's quite easy to calculate this or to determine these lattice planes when you've got a simple cubic structure, but when you have something that's more complicated, then it's not as easy. So as I say, we often just go and have a look in a database and try and match on our diffraction patterns to known materials. Okay, so what does that actually mean? How are those diffraction patterns actually produced in our diffractometer? Well, this is a very simple schematic showing just a normal reflection geometry. We often call this Bragg-Brentano geometry, so you may have heard it referred to like that before. Here's our sample. This is our source, so in our case, our copper K alpha radiation. It's directed onto the sample. The X-rays interact with the atoms and the planes of atoms in our sample, creating constructive interference, so our diffraction patterns, and then they're detected up here. So what happens on our normal Bragg-Brentano configuration is both the source and the detector are moving. So as a consequence, your penetration depth of your X-rays can be quite high. And if we're only supposed to be probing the first micron or so of our implanted region, it can be way too deep to get any signal from our implanted region. So just to hammer home that, here is a really simple schematic showing what happens in the normal configuration. Omega is the angle of our X-ray source, and this changes throughout the normal Bragg-Brentano experiment. And here is our detector, which, so the two together basically rotate through 2 theta. So this is rotating by theta, this is rotating by theta, and the combined is 2 theta. So when you get an XRD pattern, you'll see that you have your angles as a function of 2 theta. That's because it's taken into consideration both the motion of the detector and the source. So you can see here our penetration depth is way too great. This is our irradiated region. This is the rest of our sample. And it's because this angle omega is just too high. So what we have to do is we have to fix this. It's a really low angle, really shallow angle, in order for it only to be penetrating and probing that surface micron region. And this is what we do in grazing incidence. What we then have to do is calculate what our angle omega is going to be. And this is what I'm going to talk you through now. It's actually quite a relatively simple calculation. So I just do this in an Excel spreadsheet, which I'll give you an example of. But basically, the angle omega, which is the angle that we need to fix in order for our X-rays just to penetrate into our damaged region, it is calculated using this equation where X is the thickness of our region, so up to a micron. Actually, if you want to probe like the maximum DPA, so in the case of the example I gave before, so 500 nanometers, we'd set X as 500 nanometers. And mu is this thing called the attenuation length of the material. And this is a material-specific parameter. It's dependent on the composition of the material, and it's dependent on the density of the material, and it's dependent on the X-ray energy, which is why it's really important to know what is the X-ray source that you're using, because you need to input that into the equation. So the linear attenuation length basically measures the exponential decay of the X-rays as they're passing through your material. So you can define it as the length travelled before an X-ray intensity falls to 1 over E of its original value. And normally when we do the calculations, we don't just take one attenuation length, but we take 3, because that means greater than 95% of our X-rays have then been attenuated within our implanted region. So we're seeing the effect from just that implanted region. So a lot of us don't work just on single element materials. I used to work on single crystal silicon, but not anymore. Now we work on materials that have a wide range of elements. So to calculate the attenuation length for a multi-component material, whether it be steel or a ceramic, whatever it may be, you literally just find the attenuation length for every single element in that material, and you just sum them together, but you sum them weighted on the amount of each element within that material. So that's all it is. And How do you find out the linear attenuation length? Well, you can either just have a look online. There's a lot of resources out there. If anybody has done X-ray absorption spectroscopy, you'll know Bruce Revell's Hephaestus software. You can have a look at it on there, but that's may not be readily available to everybody. So I use this very simple and old school website, which allows you to input things like the density of your material in grams per centimetre cubed, the composition of your material, so I put it in atomic percent, and again, the X-ray energy. So let's just go through an example. So that diffraction pattern I showed you before, that's nice single phase BCC diffraction pattern, actually came from a multi-component, a compositionally complex alloy that has silicon, iron, vanadium, chrome, and molybdenum in. We've measured the density using the Archimedes principle. This is the real life density, and we know that our copper K alpha radiation has a wavelength of 1.544 angstroms. In the website I'm going to show you, it wants to have the radiation in terms of electron volts. So you can just use an online converter or use a conversion factor in order to convert between angstroms to electron volts. Okay, so this is the really simple thing that you see when you click on that website. So you can either enter a formula, it's got like a list of common things that you might be looking at, not for nuclear applications, I can tell you. So you just pop in your chemical formula here. So I literally put in silicon 2.3, iron 36.9, etc., etc., etc. No spaces, no units, and it understands what that means. It's now going to weight your attenuation coefficient based on the stoichiometry that you've put in here for the different elements that you've put in here. Here is our density, 7.2 grams per centimetre cubed. So this piece of software actually allows you to calculate the attenuation length as a function of photon energy. So here you're actually able to put in from one value to another value in steps of whatever you want it to be. But of course we're just using X-rays that have a specific energy, which is our copper K alpha radiation. So all I do is I just put in the same energy and just ignore the rest. So what happens then if you press submit request? You then get a graph like this, which, as I say, if you wanted to have a look at the effect of attenuation length versus photon energy, you'll see something here, but because I only put in one value, there's just one value there. So not very helpful at all. But if you go up to there where it says data file, if you click into that, it'll actually then give you the attenuation length. And again, because I only put this in, that's all it's going to give me, these values. So here is then the attenuation length. It's in microns, 5.68 microns. Okay, so we want to work out then the penetration depth or the angle of our X-rays in order to penetrate to a certain depth in our material after it's been implanted with our 5 MeV gold ions. So actually we wanted to look at a depth of 500 nanometers where there's quite a high level of radiation damage, and this is in that alloy. So we've got the attenuation length that we just found from that website, and popped it into this equation. Again, this is a nice spreadsheet. It's not as fancy as Jack's extensive 2-beam analysis spreadsheet. But here we go. It's a nice Excel spreadsheet. Pop the equation into here. So here is our copper K alpha radiation. This is the absorption length in nanometers. So it gives you in microns on that website. So make sure you convert it into nanometers. And then this is the probe depth. So you can easily change this. So I put 500 here, but you might want to put 1,000, whatever the depth of damage that you want to probe is going to be. And then it will give you the grazing incidence angle, which is calculated just using this simple equation. So 1.681 degrees. So awesome. We know our angle omega that we want to fix our X-ray source at. So how are we now actually going to carry out the X-ray experiment? Well, at Sheffield, and this is a facility that you can access via the Royce, it's a Royce piece of equipment, the Panalytical Expert. It has copper K alpha source, thank goodness. It has the nickel filter that I was telling you about to get rid of, or to suppress the copper K beta radiation. Important for proper grazing incidents is it actually has these parallel plate collimators and a secondary beam monochromator. And this basically ensures that the X-ray beam coming out of the source is parallel. When X-rays are first produced, they diverge. So what we need to make sure is, in order for them to be directed just at the angle and therefore just probing our damaged material, we need to make sure they're parallel. So you can do grazing incidence using other diffractometers, but you end up with really broad peaks as a consequence. So here we're able to make the X-ray beam as parallel as possible. There's still some divergence, but only by like 0.01 degree. And then the X-rays that are then diffracted back, again, they can diverge. So so that we have another parallel plate collimator on the other side that ensures that only the X-rays that are being diffracted from our damaged region are the X-rays that we're then using to create our diffraction pattern. So that's what's unique about this. There are some other applications from our expert. So as I said, we can do high temperature XRD. You can do things like texture and stress analysis if you wanted to do. So often there's a residual stress in materials, especially have multi-layers. And a lot of people work on thin films or coatings of materials. Coatings is suddenly becoming a quite hot topic in terms of nuclear materials design. So we're able to look at the thickness and the residual strain in coatings and implanted layers using this diffractometer. But I'm just going to show you some examples of the grazing incidence XRD. So this is what it looks like inside. Here is our X-ray source. This is our parallel beam mirror. We're fixing this at our omega angle, which is at 1.681 degrees. Here's our detector. Our detector is a thing now that's going to move through 2 theta. This is going to remain fixed. The sample is here. And this is our parallel plate collimator. So this is the thing that ensures only the X-rays diffracted from that damaged region are collected. So here's an example of some data that we get from here. This is the alloy that I was showing you before, but this particular alloy had been quenched. So it'd been produced and then rapidly cooled, and it formed this. This is actually single phase. And if I look in this paper, you can see all these peaks have been indexed. But it's a tetragonal phase, so it's a complicated, quite brittle intermetallic phase. What we found after implantation, however, using grazing incidence XRD, that just in that implanted region, it transformed into nice single BCC phase. And this phase is actually what you get when you heat up your material and you allow it to slowly cool. So basically there's residual strain and residual damage in this kind of quenched structure, but by irradiating, implanting with heavy ions, we're depositing enough energy into our alloy that either heats up the material or deposits it via elastic interactions that actually the quenched, the damaged structure can be recovered and form our single phase BCC alloy. But you don't just have to look at single crystal materials. Before we started working on metallics, we did a lot of work looking at the effect of ion irradiation, whether it was heavy ion irradiation to simulate alpha daughter recoil nuclei or alpha particle, or helium irradiation to simulate alpha particles. We did a lot of work to look at ceramic materials for nuclear applications. And this is one example of where we use extensively grazing incidence XRD to have a look at the radiation damage resistance of those ceramic materials. This is a really lovely paper by Seb Lawson. So if you're interested in having a look at radiation effects in perovskite materials, so amorphization and recrystallization and recovery, and the effect of cationic disorder in these materials, I urge you to go and have a look at this paper. So here we had the calcium lanthanum titanate system. So it's a perovskite system. Perovskites are, as Inam said earlier on, I don't know where he's gone, are kind of candidates for things like inert matrix fuels and nuclear waste forms. And we were using this as a kind of a model system to determine how cation disorder and an increased number of lattice vacancies might affect the materials, so the ceramics resistance to radiation damage, to see if we can engineer our ceramic materials to be more resistant to radiation damage. So here Seb, he produced a calcium titanate and then substituted onto the calcium site some lanthanum, because of the differences between calcium and lanthanum, that introduced lattice vacancies, as well as obviously there's introducing some cation disorder. You had lanthanum sitting on a site that should have been for calcium, for example. He implanted them with krypton and gold. I'm just going to show you the results from the 1 MeV krypton implantation. He calculated the penetration depths that we would need to use for XRD in order just to look at that implanted region. So we actually had a look at a range of different implantation X-ray angles to have a look at different implantation depths, so 0.5, 1 and 1.5 degrees. And I'm just going to show you some results from this end member down here, so 0.9. So this is where we have calcium 0.1, lanthanum 0.6, and then TiO3. So this is the cross-sectional TEM image I showed you right at the beginning. Here is our surface of our ceramic material. I've overlaid, well, Seb overlaid the trim simulation just to give you an idea of where the damage is going to be. You can't really see, unfortunately, on this, maybe you can at the back, but back here, so where this dotted line is, this corresponds to the crystalline amorphous interface. So back here, and this is what we've got the diffraction patterns on, back here we've got a fully crystalline material, and that crystalline material corresponds to the perovskite structure. And then here we've got the area rings, the diffuse scatter, which corresponds to an amorphous material. So 1 MeV krypton, these are at room temperature, in this particular ceramic has resulted in amorphization, so a surface amorphous layer being produced. Awesome. So what Seb did then was to look at the damage in this material, but using the Grazing incidence XRD, and choose different penetration depths, so choose different angles to probe at different depths below the surface, and this is what we can see here. So at 250 degrees C, at 250 nanometers, which corresponds to a depth of here, which we know from our electron diffraction pattern is amorphous, our X-ray diffraction pattern is amorphous. Awesome. If we look here at 500 degrees, I keep saying degrees, 500 nanometers, which is where we are at the crystalline amorphous interface, we see diffuse scatter from our amorphous material, but then we start seeing diffraction peaks corresponding to the perovskite structure coming through on our diffraction pattern. And then at 750 nanometers, which is way beyond here, which is when we're in our fully crystalline material, we then see the peaks corresponding to perovskite structure increasing in intensity. Now, remember, you will always get a contribution from the surface damage layer in your grazing incidence diffraction patterns, because your X-rays are coming in and then coming out. So to get to here, they've got to go through your damage layer. So you're always going to have some of your amorphous material in this case. But because of that, we're able to do some fitting or peak fitting of some of our crystalline peaks and the diffuse scatter that we see from our amorphous material. And we're able to calculate then the fraction of amorphous material that's being produced in our ceramic system. So this basically gives us a semi-quantitative way of looking at how much damage is produced in our material. And it allows us to do that without going and making loads and loads of cross-sectional TM samples and doing lots of detailed TM analysis. So this is just a really one example of where Seb did some fitting of one of the samples, the sample that I showed you before. So this is our diffuse scatter. This is the crystalline peak from the 100 perovskite structure. He fitted a pseudo-Voigt peak, but you can use a variety of different peak fitting software and basically fit to whatever is appropriate for your material. And you're allowed to then you can take the ratio between the peak and the area under the crystalline peak and the area under your amorphous diffuse scatter, and that essentially allows you to calculate an amorphous fraction. So we then plotted the amorphous fraction as a function of composition for the two different implantation conditions, and we see then that calcium titanate amorphizes produces an amorphous layer. However, when you start doping with lanthanum, so you start introducing vacancies into the the ceramic becomes more resistant to that kind of radiation damage. We attributed that to the fact that we were forming vacancies, allowing recombination or accommodation of damage more readily in these compositions. But then when you are adding in more lanthanum, you get more cation disorder, then we're seeing a lot more amorphization occurring. So this is just a really good example of not only how using Grazing incidence XRD, you can probe specific depths below your surface, and the cross-sectional TEM is in really good agreement with the Grazing incidence XRD. but it also shows you can get some semi-quantitative data out from your diffraction patterns to determine, for example, how resistant or not a material is to radiation damage. There are some caveats to this technique in that if you have a porous material, then of course your X-ray penetration depth is going to be different to the penetration depth that you calculated, because the linear attenuation coefficient assumes you have a dense material, a fully dense material. So actually in some of Seb's work, because we're working on ceramics, which weren't 100% dense, we did see in occasions the damage being a lot deeper than was predicted by our shim calculations. But shim also has those limitations as well. So that's why Seb used the 0.5 degree angle to do all these calculations, because at that depth it's quite shallow, it's just relatively below the surface. It was 200 nanometers below the surface. So hopefully that would just add some consistency into the measurement. And again, it's semi-quantitative. So that's just something to think about if you are doing these investigations. So I'm just going to leave you with this. As I said before, if you want to get access to this and other equipment that we have at Sheffield or across Royce, then please contact myself or the other technology platform leads. If you don't want to do grazing incidence but you want to do other stuff, please also let us know. We have other diffractometers that have other sources. So we have an Imperium which has a silver source, and that allows you to do pair distribution function analysis, and that's quite comparable in some ways to the neutron diffraction that we can get. And there's a lot of other things that we can do as well. So thank you very much for your time. Bang on, past, lunchtime. Thank you very much.